Here we have some data in a table. Tables are often one of the least transparent ways of presenting data. What we have is highest level of education for a population of individuals aged 25 to 34 years. This ranks less than high school, 4.7 million individuals. High school graduate, highest level of attainment, 11.8, some college 10.9, bachelor's degree 8.5, advanced degree 2.5. And I happen to know that these data are for a population of Americans in the late 1990s. We can also add up all these numbers in the left to see how many total individuals were in our total count and divide by that total to get a relative frequency. How can we visualize this? Well, one tool that I'm sure you've seen before is the bar chart. This is a really quick way to see the relative sizes of each of these bars. There's another name, a Pareto chart, named for an Italian economist. If we rank our bars from tallest to shortest, going from left to right, then that is called a Pareto chart. Another tool for describing this kind of data would be a pie chart, and this is really handy when we want to show not only the relative size of different populations, but also how they relate to the whole. This is only possible if our table lists all possible levels of education, which here it looks like it does, since we don't have a category higher than advanced degree. People with more than one advanced degree would just still be in that same category, and less than high school goes all the way down to no education at all. So each of these emphasizes different qualities of the data. It's maybe easier to compare the relative sizes of different categories in the bar chart form because rectangles are easy to look at, and it's easier to see how each subpopulation relates to the whole in the pie chart. We have a different set of tools for visualizing quantitative data. The first one we're going to look at is a stem plot, also known as a stem and leaf plot. Let's see how to make one of these, and that'll help us make some meaning from what it is. Here we have data. This is showing how many home runs Babe Ruth hit in each season from 1920 to 1934 in his professional baseball career. So we see in 1920 he hit 54 home runs. In 1927 he hit an amazing 60 home runs in a single season. And we'd like to visualize this in a more dynamic way than just this data table. So what we can do is look at the first digit of each of these numbers, and I see that the smallest is a 2, the biggest is a 6. Our first step will be to put those numbers next to a vertical line, like so. The next thing we're going to do is look at each data point one at a time and record the second digit in the appropriate place. So here I have 54. When I check off my 4, I'm going to put it in the row with the 5. The 5 is called the stem, and the 4 is called the leaf. Building up this data, we check it off one at a time. I have another result in the 50s. Here's one in the 30s, 41, 46, 25, 47, 60. We can see the data beginning to take shape as we enter more and more data from the set. Here we've entered all the data. The next step to complete a stem plot is to put each of these rows in order. So I want to switch this 5 and 2 so that the smallest numbers are closest to the stem. This is really nice that it lets us read all the data. I can see one of the data points was 22, 25, 34, 35, 41, etc. And they're all in order. We can also get a feel for the overall shape of the data and see that the most common result for Babe Ruth was to hit 40-some home runs in a season, with a maximum of 60 and a minimum of 22. Of course, some information that we lost is anything about the order in which those data points occurred. A nice application of the stem plot is the back-to-back stem plot. Here we have Mark McGwire with his career from 1993 to 2001, compared to Babe Ruth, the data that we just visualized, from 1920 to 1934. So we might ask, who was the more impressive player in terms of home runs? We can see that Mark McGwire had more of his seasons with 30-some home runs, while Babe Ruth had more results with 40-some home runs, although Mark McGwire had the single season with 70 home runs, which is 10 more than the greatest achieved by Babe Ruth. McGwire's early seasons both have very low results with 0.9. These are read backwards because they're extending away from the stem toward the left, since that's the only way to compare back to back. But each of these, one season was explainable by injury and the other by the player's strike. When we have 20 to 30 data points like this, it's not too hard to make a stem and leaf plot or even a back-to-back stem and leaf plot to compare two sets of data. But if we have a really large collection of data or data that span more than a few orders of magnitude, well, even more than one order of magnitude, it can be unwieldy to try to use a stem and leaf plot, so we have a more advanced tool that we might need software to produce. This is called a histogram. Let's take a look at what it looks like. Here we have patients who visited a clinic over the course of a day. We're listing frequency, which is how many individuals are in a category, versus the weight of that individual in pounds. And here we've defined something we call a bin width. The width of this bin is 10 pounds from 130 to 140, and notice each bin is 10 pounds wide, and every individual is in a bin. So we typically rank from greater than 130 to less than or equal to 140. So 140 would go in the left bin. Here we can see that there are 7 patients with weights between 140 and 150, and 14 patients with weights between 160 and 170. I would say, just eyeballing, that the vast majority of visitors to the clinic had weights that were between 130 and 180. And it's easy to read that kind of information about the shape of a distribution from a histogram. An important thing to note about a histogram is that there is no ideal width for bins. We have to use our judgment and try out a few different bin widths. If we had made the width of the bin 5 pounds instead of 10 pounds, these 7 would be split into 2, and maybe there would be 6 and 1 or 3 and 4, and it could have a big effect on our impression of the overall shape of the data. But every width of bin tells us something different about the shape of the data and its distribution. Histograms are absolutely the best tool when we want to know something specific about the shape of a distribution. Here we have time between eruptions of Old Faithful, a famous geyser in Yellowstone National Park, and we have 222 eruptions represented in this collection of data. We can see that there are quite a lot of eruptions that occur with a mean or average time around 80 minutes, around an hour and 20 minutes, and quite a lot of eruptions that also have a mean time around 50 minutes. So there seem to be 2 kinds of eruption that occur with Old Faithful, and further investigation might reveal something about that in some of our investigations later in the course. Data like this that have multiple peaks is called bimodal data. A mode is a local peak in the data, and the mode of the data is the absolute peak of the whole distribution. Usually if we see bimodal data, there will be something to explain why the data has that property, like there are actually 2 subpopulations with different properties. One final type of plot we can use to look at this kind of data, where we have just a single variable, is to look at how that variable changes over time. Here we're looking at Tesla prices, Tesla stock prices, and there's both a model and the actual price. And you can see that there's definitely some kind of historical feature here happening between February and April or May of 2020, which obviously has to do with the pandemic.